Welcome to this short video on Petrosys surface modelling. We're going to look at 10 good reasons for using Petrosys to model your data. We have a look at our first reason. Petrosys has the unique ability to simultaneously model multiple input data from different applications and data stores. If we just start Petrosys and we go into our surface modelling module and we open one of our gridding tasks. If we expand on this task, we can see that the input to this task actually is using kingdom seismic data as well as Petrel seismic data. So we have a look at our inputs in more detail. We've got our kingdom and Petrel inputs, but we could also incorporate seismic data from IESX and SeisWorks, which, as I mentioned earlier, are Linux-based applications or data stores, but we can actually model this data along with our kingdom and Petrel seismic data within Windows on Petrosys. We can also access well data from a range of different data stores or applications, including Geoframe, OpenWorks, again on Linux, alongside our Petrel data from our Windows data from Petrel and Kingdom, to name a few. We also are able to directly model a range of spatial data, including Oracle spatial layers, SDE layers, shapefiles, file geodatabases, and Petrel culture, again to name a few. Now, the advantage of having Petrosys access this data from a range of different applications means that we could incorporate legacy data with our current data. Say our current data is held within our Petrel project, but we want to go back and include some legacy data that was held in Kingdom projects at the time, or we get this data from a farm-in or from a data room. It's also useful for accessing alternative interpretations. So say my colleagues are working doing interpretation in SeisWorks by working a different application, maybe on Windows, something like Petrel. I can access these alternative interpretations and use them in my model building also. And it's particularly useful for regional mapping, which involves generating grids from a range of disparate data sources. If we have a look at our next advantage, Petrosys is able to handle multiple data sources in different coordinate reference systems. So we go back to our surface modelling task, expand on this. As I mentioned, we're accessing data from Kingdom and Petrel in this case, and these two data sources are using different coordinate reference systems for their projects. I can just demonstrate this by accessing our connection manager. Our Kingdom project is using WGS84 UTM31 North as its project CRS, whereas our Petrel project is using ED50 UTM Zone 31 North. So they're using a different geographic CRS. But using Petrosys, I can model both of these inputs and output one single grid in a completely different coordinate reference system. In this case, ED50 TM0 North, and Petrosys coordinate converts all the data from source and outputs in our single CRS of our chosen output grid. And this leads us into our next advantage. Petrosys is able to save all gridded surfaces directly to Petrel, OpenWorks, and Paradigm without the need for third-party connectors. If we go back to our surface modelling and we open up a relevant task, in this task we're creating a grid from Kingdom interpretation and outputting a Petrosys grid. Again, it's in a different CRS from our interpretation, but Petrosys can handle this. And then we're going to take this Petrosys grid and write it directly out into our Petrel project. Now we could also do this to Paradigm and OpenWorks. And it's not just Petrosys grid files we can write out to Petrel. We could take grids from ArcSTE, Geoframe, openworks, etc., and write these directly into our Petrel project. And we have full control over where the grid goes, what it's called, and what happens to the Z values. Do we invert them? Do we need to convert units, etc.? So if we just go ahead and run this task, connect our Kingdom project, if I open up Petrel, you can see that we have this Petrosys grid now available, built from Kingdom interpretation, available to us in Petrel for any tasks that we wish to use it for, such as stratigraphic or geocellular modelling. Also, if we open up this grid, we can have a look at the Info tab, and we've written in a certain amount of metadata with this grid into Petrel. So we know this grid was built from Kingdom interpretation. From this Kingdom project, we used one horizon. It was called Vola. The interpreter was Petrosys, and we also know what data type was used. So the advantage of doing this using Petrosys is that we can share these grids and data built from multiple input data sources with our modelling software, which would not normally have access to this data in such an easy manner. If we have a look at our next point, Petrosys offers alternative gridding algorithms which are better able to handle sparsely populated datasets. We're able to analyse input data and to deselect values which might not be required for gridding. Again, this takes us to our surface modelling module. If we open up a particular task, this task involves creating a grid from well tops which are held within our PPDM database, and we're gridding up this Rogaland formation. Now the data spacing for this well data ranges from a couple of thousand meters to tens of thousands of meters, so it's truly dense in some areas or relatively dense in some areas to quite sparse in others. If we have a look at the geometry tab, we're outputting the geometry of this grid based on a map sheet that we created. We could use any of the other map sheets in our project, or we could use the geometry of an existing grid which we created. We could scan the input data and use that to determine the output area of interest, or we can manually set the area of interest. It's important to note that you could also include a rotation angle for the output grid here as well. If we have a look at the methods tabs, we're using Petrosys standard grid and minimum curvature operation and algorithm. This is what we would recommend most people to use as a first pass. It works particularly well with sparse data such as 2D, seismic and well data. Petrosys uses a convergent gridding method which looks at all of your data all of the time through each gridding pass. This helps to maintain regional trends regardless of your final cell size. If we have a look at the faults tab, we're using faults in this gridding pass. They're coming from a Petrosys fault file, but we could directly access faults from SDE, Petrel, Kingdom, Sizewares, Sizeworks, or a shapefile, including Z values if they are present. Now, Petrosys treats faults as opaque barriers, and you have the option to include whether you wish to grid inside the faults or blank inside the faults. We could also include clipping or smoothing in this gridding pass, but I'm not going to for this purpose. We have turned on the reporting tab, which gives us a visual representation of the gridding as it happens, so we can easily identify any bullseyes or misties as the gridding goes on. And I'm also choosing to output a Petrosys contour file from during gridding. So we go ahead and run this task. We just scan our input data, so we can see the gridding, the grid as it's evolving through each pass, and immediately I've noticed there's some area of discrepancy here, or some extreme Z value that we wish to look at. So what I'm going to do is I'm going to take a closer look at this in 3 dimensions, or in a 3D viewer. And once this is once our grid draws, it's a rather large grid, including a number of faults. We can see that a grid goes down much deeper in this particular area than we would expect. So in this case, it's due to an erroneous data point. So what we can do is we can go back to our gridding process and we can choose to interrogate the input data using this sample data file action before the grid is actually output. So we can have a look in QC our input data. If I go and rerun this task then, what we do is we get a preview here in plan view, and we can zoom in and see our data points using a colour fill but also the actual value. In this case I know this data point is wrong, it's been loaded into database as an error. And what I can do is I can delete this point just using my mouse on the map. What I could also do was use a hand-picked polygon file. Say I had more than one data point I needed to edit or delete, and I can choose to action inside or outside the polygon, delete values, undelete values if I wish to undo my first delete, set these values to a constant value or clip them to within a range specified by me. In this case I don't need to change any data. What we can also do is view this data as a histogram, and you can graphically delete any points that fall within a certain histogram range. So say you had some outline noise at the extreme end of your histogram, you could graphically just click and delete that data. Now what this does is it does not delete the data from our data source, which is important. It just deletes the data from the input to gridding as an intermediate step. So what in our case I can leave my top within my master database, as to remove it or edit it I need to go through our corporate processes, but for my modelling purposes just now I just want to remove this from my modelling process. As we can see, the grid already has lost this this artifact that we saw earlier, but just to confirm we can go back to our 3D viewer and just update the view. Once that's updated, we can see that our grid is flattened out considerably. So you can see how Petrosys allows you to influence the input data to gridding without actually having to change anything within your project, without having to have multiple versions of an interpretation or a top. Just based on your different interpretation, you can actually influence that input data without changing the project or database. If we go and have a look at our next point here, with Petrosys it's very easy to configure modelling tasks which are editable sequences of instructions to help automate and simplify daily workflows or to standardise company-wide methodology. So again, this takes us to surface modelling. If I want to open up our relevant task. So this is a more extensive task than we've looked at so far. I'll just go through it and explain the different steps. I've chosen to put a log around this task, and I'll explain that in a moment. But the task itself, the first two grid create grid tasks are taking interpretation from Kingdom for two different horizons and outputting a Petrosys grid for each. We're then going to draw a Petrosys map and output a raster plot image after these first two tasks. Then we're going to use Petrosys grid arithmetic to depth convert these time grids using a formula, and again output a Petrosys map and a raster plot. We're then going to while tie these depth converted grids to tops, and then again finally draw some Petrosys maps and output some raster plots. So one of the advantages of using this tools draw map option is that it allows you to reduce the time, the amount of time spent mapping, as you can take these outputs and you can share them with someone else, such as a TA, and give them a place to start working from. So if we begin and run this task, we can see here is that I've set certain parameters for this first two tasks to be interactive. just to demonstrate that, in this case it's the cell size for the first two tasks, just to demonstrate that you can use these interactive options to share your Petrosys workflows with other people, maybe somebody who's not competent in the use of Petrosys or not familiar with the use of Petrosys, and you can expose certain parameters that you want them to change, and they don't need to be familiar with each individual panel. So if we're happy with these options, click OK to run. We're gridding up the first two interpretations from Kingdom. We're outputting some Petrosys maps and plots. We're doing some depth conversion using grid arithmetic, again producing Petrosys maps and plots. We're then well tying these two depth converted grids and outputting some plots and Petrosys maps. So our log file has popped up here. We get our log file creates an auditable trail of metadata. As you can see here, we've got a summary of our workflow, when it was run, etc. But we can have a look at in more detail each part of our workflow, and this captures all sorts of information about how this task was set up, and what parameters were used to run the task, and what the actual outputs of the task were. So in this case, the gridding passes are recorded, and things like the RMS error are captured. Now, for an auditing purposes, this gives you a full, comprehensive list of why, when, and how a particular task was run, and should allow you to justify your actions for running that task. But if we go and look at the actual outputs from our surface modelling task here, and in particular the plots that we got the software to generate automatically, I've saved these into a particular folder. So after each task, I asked it to produce a plot and Petrosys map. So in this case, we've got from the grid arithmetic depth conversion, we've got our output as a raster plot. Again, the output from the well ties on the screen here, and also from the initial 2 time gridding. So it really helps to automate your workflows. And also being able to set up your workflows like this in Petrosys allows you to run these workflows against different inputs. So in this case it was interpretation from Kingdom, but I could rerun this standard workflow, changing a few parameters against interpretation from SeisWorks or Petrel, etc. If we have a look at our next advantage, Petrosys has powerful surface modelling algorithms and mathematical operations to help interpret the subsurface. So if we go back into our same task, if we expand on the gridding of our 2 time and have a look at the methods tab, there's a wide range of operations and algorithms available to help model different situations. Say for example, we have bias, grid and polyline option here, which allow you to impose the shape or trend on an output grid. We have a localized regridding option. This allows you to regrid a small area of a larger grid which has been edited. We also have kriging and kriging with external drift options, which allow users to analyze data using a range of statistical techniques and then compute a grid based on this analysis. As I mentioned, we also have grid arithmetic capabilities. So in here we can enter any kind of formula to perform a grid-based operation. We also ship a range of templates which contain formulas already loaded, including depth conversion, geoscience examples, and mathematical functions, etc., to help you build more complex arithmetic functions. We have a look at our next advantage. Petrosys is capable of building significantly larger grids which can assist with basin-wide and regional interpretation. This requires me to go into another project I have and just go into the mapping. And I'm going to open up a regional map here that I've created, which uses a range of different inputs. These are gravity magnetic grids, a couple of topography grids, and a bathymetry grid. And these cover a truly regional scale over the whole of the Greenland area. And if we expand on our gravity magnetic grid, we can see that it contains 4,000 columns by roughly 4,500 rows. And this is in excess of 18 million grid nodes. Our topography grids contain, our topography and bathymetry grids between them contain in excess of 70 million nodes, so that's over 29 million nodes each. This really just is to demonstrate that Petrosys can easily build and handle grids of a truly regional scale. Just to give you a couple of examples, some of our clients use Petrosys to grid up basin scale mega surveys, or we have clients who are service companies who use Petrosys to create global grids. For example, global basement grids that you can buy as part of the data sets that they sell. If we go back to our advantages, have a look at number 8. When working with some interpretive applications or when performing some workflows, the quality of the surfaces output in Petrosys and contours are superior to other systems. So this requires us to go back to our other project. If I open up our 2011 project, we've got a map that demonstrates this. So in this case we've got some 3D interpretation from a Petrel project, and if I just add the outline of the grid here, so this, when we grid this up in Petrosys and Petrel, this outline represents the extent of the gridding output. So the areas to note are these areas where there's no interpretation, where the software will be left to interpolate or extrapolate trends as it sees them. So if we display our Petrel grid, well, firstly, if I just mention, we can see there's some trend, kind of northeast, southwest trend here within the data. If we display the output Petrel time grid, we can see that rather than maintaining this trend, the grid extrapolates off to the west here. There's a break in the trend. If we just compare this with the Petrosys output, you can see that there's clearly more of a trend maintained, so the grid doesn't dip down here in the middle. Now this is subjective analysis. Going by what our clients tell us, they say that we're better at modelling areas with sparse data, and especially when using faults, and we'd be interested to hear if anybody has any other examples or would like to discuss this further with us. If we go back to our advantages, number 9, use of stacking velocities and depth conversion. Which requires me to open up another project. So if we go into our velocity depth application here, we can see that we can compute velocities from your stacking velocities using a range of computation methods, including dicks and inverse dicks to produce average or interval velocities. You can also view and QC your velocities as profiles or colours in our SDF or SX editor. So example here, we've got colours displayed. We can also display these as profiles, as lines, and we can then depth convert along these lines or grid up the velocities to be used in a grid-based depth conversion in grid arithmetic. Now the advantage of doing this work in Petrosys is that you don't need to use a specialist expensive piece of software. For example, in Kingdom or Petrel there might be extra modules that you take up using this. Petrosys is a very inexpensive and simple task to complete. If we have a look at our last point, volumetrics. Petrosys contains volumetric capabilities. If we just open up a map to demonstrate this. So here we've got a simple depth structure, and we've also got two prospects outlined here using these pink polygons. What we want to do is quickly calculate some gross rock volumes for within each polygon. Now we can do this using the Petrosys surface modelling. If I open up relevant task, what you can see is we take our top grid, and reference levels or contacts that we've specified, and we restrict the volumes to the 2 prospect polygons we saw on our map. And we also have a range of options to output reports. So you can take the output volumetric information into your risking software for running Monte Carlo simulations. And we also have a range of options to output charts and a visual volumetrics map QC. Now the advantage of doing this in Petrosys is that it's quick and we don't need to use a 3D model to run these volumetrics. They're just grid-based volumetrics. So our volumetrics map has been computed here. We can see that it's calculating volumes in the correct areas, and this is our output that we've generated. So we get a very detailed volumetric output, which includes the areas, thickness and volumes for our zones across our polygons. We can then look at the totals within each polygon, but more importantly we can actually have a look at the slice volumetrics for within each polygon. In this case I used a slice thickness of 5 meters, and at each 5 meter interval throughout the structure I get reported an area, a volume for that slice and a volume above it. So I can easily adjust, if I adjust my contact level, I can, without having to rerun the volumetrics, I can see the volumes and areas involved. So the advantage of doing this in Petrosys is that we can run the volumes quickly, but also we can use it to QC volumes against other inputs. So based on the workflows I showed you earlier, these corporate standard workflows, you can include volumetrics in this and run it against different inputs or from different data sources, and you've got one standardized methodology that you can use to perform an actual comparison. We just return to our PowerPoint here. So we've looked at 10 good reasons for using Petrosys to model your data. I hope that you found this useful, and if anybody has any questions, please feel free to contact us and we'd be happy to answer these.